Video help for problem 11.12. The details for part A and part B are really given to you almost completely in the written homework advice. And I guess I don't need two writtens. And I actually want to tell you a fundamental thing that'll help you understand these things. Actually, identities like this, it's sort of like complete dephasing, except when p equals r. Let me explain. This is related to a fundamental math story that the sum of the nth roots of 1 is 0. You know, the nth roots, you take the nth root of something, you've got like x to the 1 over n, and then there's 2 over n, and then 3 over n, and 4 over n. So if I take, and the neat way to calculate roots is to realize that 1 is the same as e to the 2 pi I, and that will allow you to get all the roots. So if I sum these roots, m over n from, 0, that's the first root, and then I've got 1 over n, 2 over n, and so forth. If I sum all of them up, this will add up to 0. And this kind of math, you might say, oh my gosh, why do I bother doing this if I'm going to be an applied clinical person? This kind of stuff, you'll be surprised how many times things come up and you have to know more and more about formulas and things. And moreover, this is your mathematical statement behind perfect dephasing, because all of these different guys have different phases and they add up to 0. It's like adding up a bunch of spins in regular, in different directions. To see this, let's look at n equal 2. So you know what the root of 1 is at this point, the square root is. You've got 1 or minus 1, plus or minus 1. 1 minus 1 equals 0. In vector form, you know what? You could think of a unit circle with all the vectors adding up to 0. So for the two roots, for n equals 2, these are the two directions in a unit circle. The next, case would be the three roots. Look at the cubic roots. And if you add up these guys, they add up to 0. Numerically, I calculate 1 plus e to the 2 pi I over 3 plus e to the 2 pi I 2 over 3. And if I work these guys out, cosine 120 degrees and cosine 240 degrees and the sines and so forth, using, remember, our basic formula, e to the I theta equals cosine theta plus I sine theta, I can see how all these things, everything cancels out. As a general proof, I can use the famous geometric series. Take this m over n, bring the 1 over n inside and call that x. So this thing here to the mth equals that. Call that x. When you sum x to the m, geometric series, it's 1 minus x to the next power, that n minus 1 plus 1, over 1 minus x. I put those in, the denominator doesn't vanish, but the numerator automatically vanishes because x to the n is automatically 1. And that's just a little proof that this vanishes. Except if I had something in here, right in here, I put in another, variable. I put in another integer. I could call it, actually in here, it'll be p minus r. If I had another integer in here and I had that non-zero, this whole thing goes through again. It still vanishes. They all still dephase, unless that's 0. Of course, if it's 0, then I truly just have 1, and I just sum over all the 1s, and I get n. I get n like that. Well, I just love to try to picture these results, and this is my picture. For part B, I want to tell you the details, as I said, are just all written out for you to go through and crank through, and I think it's good. But I actually want to write the discrete Fourier pair and just let you see that, what this is? This is just like looking at the continuous Fourier transform and discretizing it, looking at an approximation of the integrals. By that I mean, you see we had G of P over L, that's G P delta K. Well, P delta K, that in the limit is sort of like K. P, we've got delta K. Think delta K real small, and then we have all the P's we need, and we cover K, in a limit. Similarly, Q delta X covers X. So I have G of K, capital G of K, little g of X. And inside here, little g of X. The sum goes to an integral. I've got e to the minus I 2 pi pq, and 1 over 2n is delta k delta x, so that this is like kx, e to the minus I 2 pi kx. Similarly, plus kx, k, go to an integral, just our Fourier transform pair.